Hello and welcome to the TI Precision Labs hands-on experiment covering aliasing and anti-aliasing filters. In this experiment, we will use a hand calculation and software tool to predict the alias frequencies. We will also use software to design an anti-aliasing filter and TINASPICE to confirm the filter's operation. Finally, we will measure the effects of aliasing and the anti-aliasing filter. For this lab, we will use the Analog Engineer's calculator and hand calculations to predict where the alias signals appear given the input frequency and the sampling rate. Next, we will confirm the effectiveness of a second-order anti-aliasing filter using hand calculations. We will then design the anti-aliasing filter using an active filter design program called FilterPro. Next, we will confirm the active filter's performance using TINASPICE. Finally, we will measure the aliasing and operation of the anti-aliasing filter. In this experiment, we will use the OPA 320 Good Filter 2 amplifier configuration with the ADS 7042. The ADS 7042 sampling rate will be set to 10 kilosamples per second. The Nyquist frequency is half the sampling rate, or 5 kilohertz in this example. Thus, any input signal with a frequency higher than 5 kHz will generate alias signals, and signals below 5 kHz will not generate aliases. The goal for this example is to predict the measured frequency for a 10.1 kHz and 0.1 kHz input frequency. First, we will use a software tool to do this calculation, then we will show the underlying algorithm. The Analog Engineer's calculator has a tool that lets you find the alias signals given the input frequency and sampling rate. The frequency range from 0 Hz to the Nyquist frequency is called the first Nyquist zone. The frequency range from the Nyquist frequency to the sampling rate is called the second Nyquist zone. The first and second Nyquist zones are repeated an infinite number of times. For example, the third and fourth Nyquist zones are copies of the first and second. This tool lets you select the number of Nyquist zones that we will observe. For this example, the input frequency is 10.1 kHz and the sampling rate is 10 kHz. This produces aliases at 0.1 kHz, 9.9 kHz, 10.1 kHz, and so forth up to 29.9 kHz. Note that there are really an infinite number of aliases, and adding more Nyquist zones will reveal more aliases. Again, we are mainly interested in the first Nyquist zone, and normally the other zones are hidden. The calculator can be downloaded using the link below, and the software can be selected by choosing Alias Calculations under Data Converters and choosing the Alias Frequencies tab. Here's the answer to the two different problems that were given earlier. These problems were both solved using the software we just introduced. For the first problem, the input signal is 0.1 kHz, the Nyquist rate is 5 kHz, and the sampling rate is 10 kHz. Since the input signal is less than the Nyquist frequency, we don't see any aliases in the first Nyquist zone. In the second problem, we apply 10.1 kHz to a system with the same sampling rate. In this case, the signal is above the Nyquist frequency and it produces an alias in the first Nyquist zone at 0.1 kHz. Remember, the EVM GUI only displays the first Nyquist zone. So if you compare the measured results for the first two examples, the FFTs will look identical. That is, for both the 0.1 kHz and 10.1 kHz signals, the FFT measurements will show 0.1 kHz. Now let's take a look at the math behind the software calculator. The alias frequencies can be calculated using the simple equation shown, where Fs is the sampling rate and Fin is the input frequency. Also, k is an integer from -n to +n, where n is the number of Nyquist zones. To find the alias, you take the absolute value of k times Fs plus Fin. On the right, you can see the example we discussed earlier solved using this method. In the hands-on experiment, we will apply a 0.1 kHz and 10.1 kHz input signal and compare the FFT results to the theoretically expected results. Before we do this, let's design an anti-aliasing filter to minimize the amplitude of the alias. Any signal above the Nyquist frequency can produce an alias. To avoid aliases, you would not intentionally apply a signal greater than the Nyquist frequency. However, you may have an unwanted noise signal at this frequency. In this example, we assume the largest input signal at the Nyquist frequency is 20 millivolts peak to peak. In fact, this signal could range from 0 volts to the ADC full scale range, but we are assuming that we will not see a signal larger than 20 millivolts peak to peak at the Nyquist. This 20 millivolt level was based on system specifications and can be adjusted depending on the expected amplitude of noise signals beyond the Nyquist frequency. In general, the anti-aliasing filter needs to reduce the amplitude of the noise signal to a level the ADC can no longer detect. That is, we want to reduce it to less than 1/2 an LSB. In this example, we want to use a simple second-order filter, so the design goal is to find a cutoff frequency that will get the proper attenuation. For example, you can see with the cutoff frequency at 100 Hz, the attenuation is about 70 dB. If we increase the cutoff frequency to 800 Hz, you will see that the attenuation decreases to 30 dB. On the other hand, decreasing the cutoff to 25 Hz gives 90 dB of attenuation. For best rejection of the alias signal, you need to move the cutoff frequency lower. However, this reduces the usable frequency range for the system. In the next slide, we will consider the math involved in selecting the best cutoff frequency to give us the required attenuation. First, remember that we need to attenuate the signal to less than 1/2 an LSB. Solving this for a 12-bit ADC with a 3-volt full-scale range gives us 366 microvolts for half of 1 LSB. The required gain can be calculated by dividing half an LSB by the amplitude of the alias signal. In this case, the gain is 18.31 millivolts per volt, or minus 34.7 dB. The gain equation for a second-order Bessel transfer function is given. We need to solve this equation for 18.31 millivolts per volt at a frequency of 5 kHz. Unfortunately, this equation doesn't have a simple closed-form solution and needs to be solved numerically. This will be true for most filter problems. In the next slide, we'll introduce a software tool to solve this problem. This software tool finds the cutoff frequency for an anti-aliasing filter given the filter type, filter order, Nyquist frequency, input alias signal amplitude, ADC full scale range, and the ADC number of bits. For this example, the software calculated a 534 Hz cutoff frequency will produce a minus 34.75 dB attenuation at the Nyquist frequency. This attenuation will reduce the 20 millivolt alias to 1/2 of an LSB. Thus, the filter will attenuate the 20 millivolt signal to a point where the ADC can no longer detect it. Using this approach, we fixed the order of the filter to 2 and adjusted the cutoff frequency to achieve the desired attenuation. Another approach is to fix the cutoff frequency and adjust the filter order to achieve the desired attenuation. Let's take a look at that. Here we will solve the same problem as before, but the cutoff frequency will be fixed at 500 Hz and we will find the filter order needed to achieve the desired attenuation. From the previous problem, we saw that the attenuation was minus 34.7 dB. From this graph, you can see that a first-order filter doesn't meet the attenuation goal. The second-order filter meets the attenuation target exactly, so this is what we would use in a design. Using a higher-order filter would provide even better attenuation, but this would add complexity and cost to the circuit. On the next slide, we'll take a quick look at a software tool that finds the anti-aliasing filter order given a fixed cutoff frequency. This tab in the Anti-Aliasing Filter Designer finds the filter order given the filter type, Nyquist frequency, cutoff frequency, input alias signal amplitude, ADC full scale range, and ADC number of bits. For this example, the software calculated a second-order filter will produce a minus 34.75 dB attenuation at the Nyquist frequency. The two tabs provide two different ways to solve the same problem. For example, if your design needs to be limited in cost and complexity to a second-order filter, you can use the tab that solves for the cutoff frequency. On the other hand, if you can use a more complex filter but need a specific cutoff frequency, you can use the tab that solves for filter order. For this example, we know the filter type, filter order, and filter cutoff frequency. In the next slide, we'll introduce a software tool that will select filter component values to realize this filter. Pause and run the Analog Engineers Calculator anti-aliasing filter design software. Filter Pro is a free active filter design program from Texas Instruments. This software can be downloaded using the provided link. We will use this software to find components to realize our second order 500 Hz Bessel filter. Once you have downloaded and installed the software, it can be run under All Programs, Texas Instruments, Filter Pro Desktop. The first screen you will see in Filter Pro is to select the filter type. In this case, we want a low-pass filter. Press Next and we can enter the filter specifications. In this case, we want a gain of 1 and a cutoff frequency of 500 Hz. The ripple specification isn't really pertinent as we are using a Bessel filter and Bessel filters don't have ripple. Finally, check the filter order as Set Fixed and select a second order filter. Press Next to continue. Now we will choose Bessel for the filter response type. Bessel has a maximally flat response and linear phase. Bessel and Butterworth are two commonly used filter types for anti-aliasing applications. For more details on filter responses, use the link to the document at the bottom of the page. Press Next to continue. In step 4, we will choose the filter topology. In our example, we need a non-inverting configuration, so we will use the Sallen-Key filter. The multiple feedback filter, on the other hand, is an inverting topology. The link at the bottom of the page also covers details on the differences between the various filter topologies. Press Next to continue. Now we have a schematic with values. However, by default, the values are exact values, and we really need standard resistor and capacitor values. Using the pull-down menus, we can change the resistors to 1% resistors and the capacitors to 5% capacitors. Furthermore, we can edit the component values, and all the components will scale accordingly. In this example, we changed the 150 nanofarad capacitor to 10 nanofarads, and all other components scale to the appropriate standard value. This is a useful feature as a 150 nanofarad capacitor is not available as a COG type, but 10 nanofarads will work for COG. Here we see the final circuit with its associated graphs. The final output doesn't take into account the non-ideality of the amplifier. For this reason, it is always recommended to simulate the circuit in TinaSpice for final confirmations. Pause and run the Filter Pro software. This slide shows the TinaSpice frequency response for the filter that we designed using Filter Pro. Note that the cutoff frequency is at 500 Hz as expected. You can also see that the roll-off is at 40 dB per decade, which is what you would expect for a second-order filter. Finally, we show the results for a transient simulation for a 2.9 volt peak-to-peak signal at 10.1 kHz. 2.9 volts is used as it is nearly the ADC full-scale range. The reason 2.9 volts is used rather than 3 volts is to avoid the nonlinear region of the amplifier and to avoid overdriving the ADC. The output of the transient response is 11.6 millivolts peak-to-peak. This is what you would expect based on the attenuation at 10.1 kHz. The equation shown here is another way you can calculate the expected output at 10.1 kHz. Note that the transient simulation and hand calculations match. The same approach can be used for other signal frequencies and amplitudes. Later, we will fill in a table for several different amplitudes and frequencies. You might have noticed that the output signal appears to be inverted even though the circuit is a non-inverting topology. This inversion is actually a phase shift introduced by the second-order filter. Pause and run the TinaSpice simulation. At this point, we are ready to start the hands-on experiment. We will be comparing two different circuits. The first circuit we will look at is called OPA 320 Good Filter 2. In this case, the filter at the output of the OPA 320 is not an anti-aliasing filter. This filter is designed to minimize the transients from the ADC charge kickback that occurs during conversion. We will discuss the design of this filter in detail in a later Precision Labs video. For now, it is important to note that this filter's cutoff frequency is 9.1 MHz, and so it will not work as an anti-aliasing filter as the Nyquist frequency is 5 kHz. The next circuit we will look at is a Sallen-Key filter. This is the circuit we designed using the Analog Engineer's calculator and FilterPro. The cutoff here is 500 Hz and the Nyquist frequency is 5 kHz, so this circuit will attenuate any alias signal by at least 35 dB. We will measure the effectiveness of this filter in the hands-on experiment. Let's get started. For this experiment, we will be using channel 3 on the Precision Labs hardware. First, set the jumpers as shown here. Next, install the OPA 320 Good Filter 2 coupon card into the channel 3 socket. This is the amplifier that will not have an anti-aliasing filter. Connect the PSI to the PLabs board using the SMA cable, and connect the PHI to the PLabs channel 3 connector. Finally, connect the USB cables to the computer. Pause and connect the hardware. Now let's start the software by selecting the PLabs Power Scaling EVM icon from the Start All Programs menu. Once the software is running, you should notice the green Hardware Connected message at the bottom of the software. Next, change the number of samples to 16,384. Next, change the sampling rate to 10 kilosamples per second. Finally, press here to expand the controls for the PSI hardware. Pause and get the EVM software started. Now we can apply a 0.1 kHz and 10.1 kHz signal to the ADC and look at the response. These are the signals that we used in the alias calculator earlier. Based on our earlier results, we expect to see a 0.1 kHz signal for both input frequencies. The 10.1 kHz input signal should produce a 0.1 kHz alias signal. First, enter the input frequency of 0.1 kHz. Set the amplitude to 2.9 volts, and set the offset to 0 volts. Press Update and turn on the output. Press Capture and you should see the output signal. Left-click and drag on the time domain display to zoom in on the signal so that 200 samples are visible. The horizontal axis can be converted to time. The time for each point is equal to 1 divided by the sampling rate. For this example, 1 divided by 10 kHz is equal to 0.1 millisecond per sample. The number of samples between the two peaks of the input signal is 100 samples. The 100 sample period multiplied by the 0.1 milliseconds per sample gives a period of 0.01 seconds for the digitized signal. Taking the reciprocal of the period, we get the expected 100 Hz. Next, enter the input frequency of 10.1 kHz, set the amplitude to 2.9 volts, and set the offset to 0 volts. Press Update and turn on the output. Press Capture and you should see the output signal. Left-click and drag on the time domain display to zoom in on the signal so that 200 samples are visible. Notice that the period of the 10.1 kHz signal is the same as the 0.1 kHz. This is because the 10.1 kHz signal actually produces a 0.1 kHz alias frequency. Here we compute the peak-to-peak amplitude for the digitized waveforms. Both waveforms are about the same amplitude and close to the applied signal. The difference between the applied signal and the digitized signal is due to system inaccuracies and loading of the signal generator. Now let's take a look at the frequency domain. Here we show the frequency domain response for the 0.1 kHz and 10.1 kHz input signals. As you might expect, both signals have essentially the same frequency domain result. In both cases, the measured fundamental is at 0.1 kHz. Clearly, the 10.1 kHz signal aliases to 0.1 kHz. Pause and capture the time domain and frequency domain signals for both the 0.1 kHz and 10.1 kHz signals. Now let's do the same experiment for the Sallen-Key filter. The only change needed for the hardware is to change the coupon board from the OPA 320 Good Filter 2 to the Sallen-Key filter. Pause and install the Sallen-Key filter. Here we apply a 0.1 kHz and 10.1 kHz 2.9 volt sine wave to the input of the Sallen-Key filter. Recall that this filter has a cutoff of 500 Hz, so the 10.1 kHz signal should be significantly attenuated. After capturing the signals, you can see that the 0.1 kHz signal is passed through the filter and the 10.1 kHz signal is no longer visible. To zoom in on the 10.1 kHz signal, change the Y-scale fit to auto mode. Once you change the Y-scale fit to auto mode, you can see that the alias signal is still present. The peak-to-peak value can be calculated by subtracting the maximum and minimum voltages. In this example, the peak-to-peak is about 12 millivolts, which is very close to the predicted 11.6 from simulation. Pause and apply the 0.1 kHz and 10.1 kHz 2.9 volt signals to the Sallen-Key filter. This table summarizes the results of the different anti-aliasing experiments. We have completed the first 4 experiments. In the first experiment, a 0.1 kHz 2.9 volt peak-to-peak signal is applied. The captured data shown in this example measurement approximately matches the input signal. Here, the differences are due to loading of the PSI signal. The exact value of your measured results may differ somewhat, but it should be close to the example shown. In the second experiment, a 10.1 kHz signal produces an alias signal at 0.1 kHz. In the third and fourth experiment, the Sallen-Key filter is used to minimize the alias. Using simulation, we predicted that the alias would be attenuated to 11.6 millivolts, which compares well to the 12 millivolt example measurement. Again, your results should be similar to this. In the last 2 experiments, we will verify the design of the anti-aliasing filter. Recall that we designed the filter to attenuate a 20 millivolt input signal at the Nyquist frequency to an amplitude of less than 1/2 an LSB. Let's test the anti-aliasing filter just beyond the Nyquist frequency at 5.1 kHz. The attenuation at this frequency is minus 36.1 dB, so the expected output for the 20 millivolt input signal is 313 microvolts. The plots here show the time domain and frequency domain output. We expect the 20 millivolt signal to be completely attenuated. Looking at the time domain signal, we see about 3 codes of noise, or 2 millivolts peak to peak. You can't really see anything that looks like a sinusoidal signal in the noise. Nevertheless, if you look at the spectral analysis, you can see a small component at 4.9 kHz, and this is where you would expect to see an alias of the 5.1 kHz input signal. For all practical purposes, however, the signal is very small and difficult to distinguish from the noise floor. Thus, the filter is working as expected. Let's confirm the attenuation by applying a full-scale signal. Here we use the same configuration, but change the input signal amplitude to 2.9 volts. The attenuation at 5.1 kHz is 36.1 dB, so the expected output can be computed to be 45.4 millivolts. Applying the signal and measuring the peak-to-peak output shows that the filter attenuates as expected at 5.1 kHz. Now we can fill in the results for the final 2 experiments. Note that the measured results for the filter closely match the expected results. Pause now and make the measurements for the final 2 tests. That concludes the hands-on experiment. I hope this was useful to you. Thanks for your time.